Let's consider the following problem. Consider 4 identical point charges arranged in a square below. Show the electric field at the midpoint of each square points outward from the center of the square and calculate its magnitude. Now, this square is what we call perfectly symmetrical. Just Q plus Q plus Q plus Q. Alright, so these are all 4 squares, right? And so if you basically want to calculate the force or the electric field, right, say here, this will be the same in all 4 corners, because if I rotate the square by 90 degrees, I must get the same answer over and over again, right? Okay. So this is the first example of what we call a symmetry argument. We use the fact that this square has fourfold symmetry, right? You can rotate 4 times, bend it over and stuff like that to basically get an idea of what the electric field has to be, right? So what this says is that at the end of the day, all I need to do is calculate just one side, and once I get one side, I could just reproduce it in all 4 sides. All right. So let's suppose I have some electric field there. I don't know which direction it's going to point in yet. All right. All right, but there's some electric field there. All right. So I'm going to just basically do it for this point first, and then once I do it for this point, I'm just going to rotate it around and then draw what the necessary electric field has to be for all 4 sides now. Okay. So the electric field here. Well, let's label all the point surges number 1, or charge number 2, number 3, and number 4. So this would be due to the electric field from number 1, the electric field from number 2, the electric field from number 3, plus the electric field from number 4. Right? I call this point O here to be 1 on O, 2 on O, 3 on O, and 4 on O. Okay. All right. So let's just do this very carefully here. Okay. Let's endow this with a coordinate system here. So this will be my x vector. This will be my y vector. All right. Okay. And let's give this as a square. So we'll just call each side length d. It doesn't really matter, right? All right. So let's calculate the electric field from. We're going to do a simple example first. We're going to do basically 3, 0 and 4, 0. Okay. So electric field from 3, 0. Well, that's just going to be the Coulomb's constant, charge Q3 divided by basically the distance from R30 square R30 hat. Okay, but what is R30 hat? R30 is this distance right here, R30 vector, which is going to be basically minus d over 2, because each side is length d, so this is half this distance, in the y hat direction. The negative sign just accounts for the fact that it's pointing in down, right? Okay, so this is just going to simply be k plus q divided by r30 is just going to be d over 2 squared in the minus y hat direction. Okay, now if I do the same thing for number 4, I know everything's almost the same. E40 is just going to be basically k q4 over r40 squared r40 hat. Now the only this distance is d over 2, but rather than being minus y hat, this term is going to be pointing in the same direction as y, so it'll be plus y hat, right? And so if you plug this in again, this is going to be basically k q. Now this is going to be a d over 2 squared in the y hat direction, right? Okay. So if I look at these two things, all right, if I add E30 plus E40, this is negative, this is positive, these two terms will go to 0, okay? Which is nice, right? But you can also see that, right? If you're midplane between these two vectors, right, the electric, and they're two of the light sign, the electric field is going to cancel itself in the center, between these two at least, right? So now we're left with basically 1 and 2, right? So let's calculate the electric field from 1 on 0. Well, this is just simply going to be equal to k q 1 over R10 squared, R10 hat. Now, the tricky part is getting R10 hat correctly, right? So, what is that direction? So, let's just draw this out very carefully. So, this is, drew very well, R10 vector, okay? And R10 hat will be something in this direction, all right? Now, there are two ways of looking at this problem at this point, right? The first way is to basically try to figure out this angle here, right? But there's another way of doing this, right? Which is basically figuring out this length here and then getting this sine. Because really, what you really care about is the sine of the angle or the cosine of the angle. You don't really care about what the angle is necessarily, right? So this is just going to be, let's just write this thing out here. K positive Q R10 squared, which we're going to figure out in a second. And then this hat term is just going to be, let's call this angle theta here, sine theta in the minus y hat direction plus cosine theta in the positive x hat direction. Okay, like I said earlier, we don't really care about what the angle is. We just care about what the sine and cosine of the angle is. And what's the sine of the angle? The sine of the angle is just going to be this term, this side, divided by the length of this vector here, which is R12. So sine is this side, which is actually d over 2, as stated earlier, divided by R10. That's beautiful. And this side is going to be basically just be d divided by R10 again, right? And what's R10? R10, well, it's just this side plus this side. That's going to be equal to the square root of d over 2 squared by Pythagoras' theorem plus d squared. Okay, so this is going to be basically the square root of 5/4 times d. All right, because the 1/4 here is a 1 plus 1/4 is a 5/4. Take the square root. That is square root of 5/4 times d. All right. All right. So if we basically put this all together for E12, K Q 5/4 squared is 5/4. Square root when you square it, d squared. Okay, and then this is just going to be d over 2 divided by square root of 5/4 d in the minus y hat direction plus d over square root of 5/4 d in the x hat direction. All right. Okay, and so if I simplify this all together, d's will kill each other. This d will kill each other here. This becomes basically square root of 5/2. This also becomes square root of 5/2. And so if I were to write everything out, this just becomes 4/5. So inverting this guy right here. K Q squared over d squared. Okay, this one, the halves will cancel out. Will be basically minus y hat over square root of 5 plus 2x hat over square root of 5. Okay, that's the first part. Okay, now let's get the second part. E, basically 20 vector, will be K Q2 over R20 squared, R20 hat. So you notice, because of this beautiful symmetry in this problem, this is R10, R20 vector. Okay, this thing is just basically this almost the same, but with different signs. So let's do this correctly. So it's going to be, is it K Q2 is just positive Q divided by R12. Well, that's just going to be the same distance as R10 because of the symmetry of the problem. So this would be 5/4 d squared, okay, times sine of theta. Now the only difference is this point in the positive y direction, y hat, plus cosine theta in the positive x hat direction again, right? And again, we figure out what these angles are going to be, right? This is going to be equal to, let's just simplify this out, 4/5 kq over d squared. This angle right here is just going to be sine is d/2 divided by square root of 5/4d, as we stated earlier, y hat direction, plus d over square root of 5/4d in the x hat direction, right? So if you simplify this all out, this is just going to be 4/5 kq over d squared. Okay, this is going to be y hat over square root of 5 plus 2x hat over square root of 5. Okay, so now we knew from earlier that the electric field from 3 and 4 will cancel each other, and so we are just left with the electric fields adding up the electric fields from 1 and 2, right? So the electric field is going to be E10 plus E20, because we know that the electric field from 4 and from 3 are going to add up to 0, so we don't have to account for that, right? So this, you know, is because the 4/5, everything out in front. Let's just basically glum everything together. So 4/5 kq over d squared, right? That's the common factor in front of everything. Okay, so let's do number 10. That's minus y hat over square root of 5 plus 2x hat over square root of 5. And then this one, 20, is going to be, again, y hat over square root of 5 plus 2x hat over square root of 5. You notice that these will cancel each other out, and then you're left with this. These two means the same as each other. So if you basically put it together, it's going to be 4 times 4 is 16. 16 over 5 times the square root of 5 k q over d squared in the x hat direction. Okay, so what that means is that this electric field points out perfectly in the x hat direction, all right, and it has this magnitude, right? 16 divided by 5 times square root of 5 kq over d squared, right? That is the magnitude of that particular vector. Now if I turn it around, okay, this thing has the point, it's the same problem as before, so again we get this vector. Turn around, it's the same problem as before, so we have to get this vector. Turn around again, it's the same thing as before, and so we have to get this vector, right? And so at the end of the day, you're basically left with the following problem, because it's a symmetrical problem, right? You only need to do it once, right? I calculated here by argument of symmetry. This is the same vector in this direction, this is the same vector in this direction, this is the same vector in this direction. And so basically the electric field at the midpoint of each square points outward, and we have the magnitude of the electric field. Okay, I hope that was helpful.